Today we're going to take a look at continuing our discussion about finding mins and max. Today finding the absolute extrema, or the absolute min or max. On an entire interval. Up until this point, we've been interested in just finding local mins and local max. But now what we're going to take a look at is if we've got a function that goes from a point here, goes down to up to a point here. What we're going to be interested in is where the absolute max or the absolute min takes place. And so you might notice down here at the bottom of this valley, that is the absolute lowest point on the graph. Similarly, the endpoint on the right is the absolute highest point on the graph. So that might be another point we were interested in. We could even see just like a line segment with two endpoints. As long as it's got these endpoints, we're going to see an absolute max at the top and an absolute min at the bottom. So they might both be endpoints. Or maybe neither of them are going to be endpoints. For example, consider a graph that goes up and then down and then up and then stops. What we see is the absolute highest maximum point is at the peak, and the absolute min lowest point is at the valley. And so you can kind of see that these absolute min or maximum points occur either at a critical number remember that's when f prime of x is equal to 0, or an endpoint. Or there's one more possibility, and that's when f prime of x is undefined. There's sometimes when the entire function is defined, but the derivative is not defined. And we'll look at an example of that in a little bit. So let's see if we can find a few absolute extrema, and then we'll get to the more interesting problems where we actually apply them to some situation. Let's say f of x is equal to x to the 8/3 minus 16 x to the 2/3. And it is on the interval -1 through 8. And we want to find the absolute maximum and the absolute minimum of this function. Well, we know it could happen at a critical point, and that critical point is at f prime of x. Taking the derivative, we have 8/3 of x to the, subtracting 3, 5/3. Minus, we're going to have x to the -1/3, and then we're going to multiply 16 times 2/3. 16 times 2 is 32/3. And when this function equals 0, we've got a critical point, which may or may not be the absolute min or the absolute max. So let's solve this. One thing I notice is everybody's got a third. Also, everybody's divisible by 8. So I'm going to factor out the greatest common factor of 8/3. Leaves behind x to the 5/3 minus 32 divided by 8 is 4. And I'm going to move the x to the 1/3 to the denominator. In fact, to make life easier for us, let's just go ahead and multiply both sides by that fraction 8. The reciprocal of that fraction, 3/8, just gets rid of it. It is gone. We have x to the 5/3 minus 4 over x to the 1/3 equals 0 times anything is 0. And then to make life easier for us as we solve, let's clear that denominator by multiplying each term by x to the 1/3. And when we do, we get x to the 6/3 or 2 minus 4 equals 0. And now you can see pretty quick that's x plus 2, x minus 2 equals 0. And so we now have our critical points, x equals negative 2, x equals positive 2. So these are two possibilities about where the min or the max could occur. There's another possibility, though. Remember, we've got to check the endpoints. So let's go ahead and clearly state those are the critical points. We've also got endpoints, which are negative 1 and 8. And we've also got the undefined points, where f prime is undefined. And you notice that we've got an x in the denominator of our derivative. That denominator cannot be 0, so it is undefined when x equals 0. So we need to check all of these points. Negative 2, 2, negative 1, 8, and 0. One of them is going to be our critical point. So let's use our calculator to do the dirty work. Pulling up our calculator, we'll hit y equals to put the equation in. We've got x raised to the, and we're going to need to do 8/3. You may have to do that in parentheses if you have a TI-83. So it's supposed to be x to the 8/3. X to the 8/3. There we go. Minus 16x to the 2/3. And again, on 83, you have to put that in parentheses. And hit enter. And we're going to hit second table. And we're going to type in the values that we want. We want negative 2, enter, 2, enter. We also have some endpoints that we need to check. Let's move our calculator over so we can see. Negative 1, enter, 8, enter, 0, enter. And then I can look at these values to find the minimum. One thing I want to notice as we look at these values, don't forget about the original domain that we were interested in between negative 1 and 8. This first point of negative 2 is outside of that domain, so we actually don't really care about that point. We do care about 2, negative 1, 8, and 0, and we see the minimum occurs at 2, negative 19. The maximum occurs at 8, 192. So we're going to say the absolute minimum occurs at 2, negative 19.05. And the absolute maximum we found out occurred at 8, 192. So to find these absolute extremes, we were looking at three things. Critical numbers, where the derivative is 0. Endpoints. And also, if the derivative is undefined, we also checked those points. Let's do one more example, this time without a specific domain. How about f of x equals 3x to the 4th minus 4x cubed minus 12x squared plus 2. No domain, so we're really going to be considering everything. If no domain is given, we're going to assume we're going from negative infinity to infinity. So first we look for the critical numbers. F prime of x is equal to 12x cubed minus 12x squared minus 24x. Factor out the GCF of 12x, leaves behind x squared minus x minus 2. Again, we want it to equal 0. That's a critical number. Continuing to factor then, it's x minus 2, x plus 1 equals 0. And so we now know our critical points, our critical numbers, are x equals 0 from the 12x, positive 2, and negative 1. We also want to check the endpoints. The endpoints here are going to be positive and negative infinity. So what we want to do is we need to look at and consider the limit as x goes to infinity of our function f of x. Well, as x goes to positive infinity, we know 3x to the fourth, that's a fourth power. It's going to come in from the top, wiggle a bit, and go up to the top. As x goes to infinity, this guy goes to infinity as well. As x gets huge, this guy gets huge, which means there is no maximum on this graph, because we know it's going to go forever up on both sides. We might even want to consider the limit as x goes to negative infinity. On the right side, it also goes to infinity on both sides. Sometimes it'll go to positive and negative infinity. The big thing here we're seeing, though, it goes up forever. There is no absolute maximum. The only other thing to consider is where f prime might be undefined, but it's a polynomial. We know polynomials are defined on all real numbers. So really, all we have to check, looking for the minimum, because there is no max, we're going to check these three critical points on our calculator. So we'll hit y equals and clear out the old function. It's 3x to the fourth minus 4x to the third minus 12x squared plus 2, second table, and we're testing 0, 2, negative 1. Delete out the other ones so we don't get confused by them. 0, 2, negative 1. We know there's no maximum. We're looking for the minimum, which we can see happens at negative 30. So we have a minimum at 2, negative 30. And that's how the first derivative and the endpoints help us find where the absolute min and the absolute max of a function is going to be. But that's boring because those are just functions and equations. We're really interested in finding some applications where we are trying to minimize or maximize a situation. So taking a look at that, let's do a really basic, almost too mathy example to see the process, and then we'll get to more interesting examples. We're going to find two non-negative numbers, x and y, such that 2x plus y equals 30, and xy squared is maximized. This first equation, because it's got an equal sign on it, that's called our constraint. That's what we're limited by. The second function without the equal sign, what we're trying to maximize, that's our objective function. Our objective is to make that as big as possible. We're going to use the constraint to help us find that. The easiest way to solve this would be to probably solve for the y. If we subtract 2x from both sides, we get 30 minus 2x. And we're going to plug that in for the y. So we've got x times 30 minus 2x squared. Well, we know how to square something. We could square it, and we get 900 minus 120x plus 4x squared. Distribute that x through, we get 900x minus 120x squared plus 4x cubed. And if we want to maximize this function, we need to take the derivative, and set it equal to 0. The derivative is 900 minus 240x plus 12x squared. We make it equal to 0. Factoring out a GCF of 12, also I'm going to rearrange the terms so that the x squared's in front. So 12 out of there is x squared minus 20x plus 75. Factoring out then, x squared is x and x. 75 is 15 times 5. If we couldn't do that, you could have used the quadratic formula. That also works if you don't know how to factor it. But either way, the important thing is that x equals 15 or 5. One of those is going to maximize our function. So, quick way to do that is to figure out which one does. We probably need to know some, well, I guess the function after we substituted in was x times 30 minus 2x. So we'll go second quit. We'll hit y equals, clear out the old function, and we'll type in x times 30 minus 2x, close the parentheses, squared. Enter. Second table. Delete out the values we don't want. We're testing either 15 or 5. Which one's going to maximize us? Notice 15 gives us 0. That's probably not the maximum. 5 gives us 2,000. 2,000 is our maximum. So 2,000 is the maximum when x equals 5 and y equals, well, remember y was 30 minus 2x. 30 minus 2 times 5 is 20. So when x is equal to 5 and y is equal to 20, we have a maximum of 2,000. The idea and process here is going to be the same every single problem. We'll look at our objectives and our constraints to build a function that we'll take the derivative of and set the derivative equal to 0. Let's try another example. Let's say I have a raging river here, and I've got a man over here, and he wants to get to his house, which is on the other side of the river. To get there, he's going to go run along shore, and then he's going to boat across the river. So that's his path. Here's some constraints, though, to limit us. He's got to get a horizontal distance of 300 feet. He's also got to cross a river, which has a vertical distance of 800 feet. This is not to scale, you might have noticed. The catch is you can run a lot faster than you can swim. He's going to swim across the river. He can run, let's make him run 160 feet per minute. And he can swim, let's make him swim 70 feet per minute. And the question's going to be, how far should he run before he turns to swim, if we want to minimize the time? He wants to get home as quick as possible. How far should he run? How far should he swim? Well, I'm going to draw this diagram a bit bigger so that we can see an entire triangle here. Maybe even a little bit more to scale. Actually, I'm going to delete that one. And so we've got 300 feet along shore, 800 feet vertically. He's going to go part way across and then go up. So we need to label this bottom part a bit more clearly because we know the entire distance here is going to be 300. And to make life easier for us, we're going to label this right side of it just x. So if the entire distance is 300, the right side is x, how much remains on the left side? Well, there's 300 total. We subtract off the x that's on the right side, and that'll tell us what's on the left side. We are also interested in the distance he travels diagonally, which is the hypotenuse of a right triangle. And we know a right triangle is a squared plus b squared equals c squared. So if we do x squared plus 800 squared, that's going to equal c squared. Take the square root of both sides, and c is equal to the square root of x squared plus 800 squared. That side is the square root of x squared plus 800 squared. Those are our distances. We want to minimize time. You might remember that distance is equal to rate times time. And we want to minimize the time. So how do we get the time alone? So if we divide both sides by the rate, we find the time is equal to the distance divided by the rate. We just calculated the distances, and we've been told the rates. So the time of x function is the distance. The first distance he runs is 300 minus x. Divided by the rate, he's running along stream, 160 feet per minute. In addition to that, he's going to swim a distance of the square root of x squared plus 800 squared. Divided by the rate there is 70. So if we want to minimize his time, we need to minimize this function. We need to take the derivative and set it equal to 0. T prime of x is equal to, that 160 in the denominator is a constant, so I'm going to pull that out front. 160 times the derivative of the numerator, which is just -1, plus that denominator of 70 is just a constant, so I'm going to bring it out front, times, we think about square roots as a fraction, 1/2 exponent, so we have 1/2 times x squared plus 800 squared. Oops, 800 squared. Square the 800, not the whole thing. If my eraser will work. 800 squared. All that to the -1/2. Times the derivative of the inside, which is 2x. A little cleaning. The 2's are going to divide out. So now we have t prime of x equals 1 over 160 negative plus, in the numerator, all we're going to have left with is the x, because the 70 and the x squared plus 800 squared to the 1/2 is on the bottom. Set that equal to 0. And let's move the 1 over 160 the other side. X over 70 times x squared plus 800 squared to the 1/2 equals 1 over 160. Let's see. Let's cross multiply everything. Get rid of all the fractions. Cross multiply. So we've got 160x equals 70 times x squared plus 800 squared to the 1/2. Something I notice here to make life easier for us is both sides have a factor of 10. So I'm going to divide both by 10 just to make the numbers easier to work with. We don't have to do this step. We'd get the same answer either way, but this will just make the numbers more manageable. 16x equals 7 times x squared plus 800 squared to the 1/2. And then, still in the spirit of making it easier to work with, let's go ahead and square both sides. Get rid of that 1/2 exponent. So 16 squared is 256. X squared equals 7 squared is 49 times x squared plus 800 squared. Distribute through the parentheses. 256x squared equals 49x squared plus, we'll have the calculator do this later, whatever 49 times 800 squared is. That'll keep life easier for us. Subtract 49x squared from both sides. Getting all the x squareds on one side. 256 minus 49 is 207. X squared equals 49 times 800 squared. We'll divide both sides by 207. We have 49 times 800 squared divided by 207. And we can get our answer simply by taking the square root of both sides. And we will let the calculator do that dirty work. Let's see. That is the square root of 49 times 800 squared divided by 207. Enter 389.2. Wait a minute, what's wrong with 389.2? Go back to our picture. We only had 300 feet worth of space to work with. That's outside of our domain. He's either going to run 0 to 300, but definitely not more. He's not going to pass his house and swim back. That wouldn't make sense. So this is outside of our domain. The only thing left to check are the endpoints, f of 0 and f of 300. He's either going to swim the whole way or run all the way across and swim up. Which is it going to be? Well, the function to stick in our calculator. Recall this was the time function, so let's get that in our calculator. Y equals, clear out the old function, parentheses around the numerator, 300 minus x, close the parentheses, over 160, plus the square root, parentheses, well, I guess we don't need parentheses, x squared plus 800 squared. Get out of the square root. That either involves closing the parentheses or scrolling out, depending on the type of calculator you have. Divided by 70. Enter. And now we're going to check those endpoints of 0 and 300. Second table. 0 and 300. Notice 300 gives a time of 12.2. Oops. 12.2 is the minimum, which means it's going to be best for him to run all 300 meters and then swim across. Otherwise, he'll slow down too much. Let's try another one. Let's say in a theater, it is estimated that if 50 seats are full, profit per seat will be $6. However, profit per seat will decrease 10 cents for each additional seat sold. How many seats should be filled to maximize profit? So we're looking at profit. Profit, you notice, is going to be the number of seats times the per seat profit. That'll give you the total profit. And right now, we're saying at 50 seats times the per seat profit of 6, our profit is 300. However, that's going to adjust. We're going to increase the number of seats, but we don't know how much by. So we're going to say 50 plus x. We don't know how many seats we're going to increase, but when we do that, the price per seat is going to decrease or subtract 10 cents, 0.10, for every x, or for every seat. This, then, is what we want to maximize. Find our maximum profit inside these constraints. Well, we could take the derivative of the product, but polynomials are easier, so let's multiply this out. 6 times 50 is 300, minus 50 times 0.10 is 5x, plus 6x minus 0.1x squared. And so when we combine like terms and reorder it, we get negative 0.1x squared plus 1x plus a 300. And this is our function that we're going to want to take the derivative of. The derivative of that's going to be negative 0.2x plus 1. We set it equal to 0. And we can solve this really quick. Subtract 1 from both sides. Negative 0.2x equals negative 1. Divide by negative 0.2, and x equals 5. We need 5 additional seats to maximize profit. That's a total of, we started with 50, with 5 additional, total of 55 seats. How much is that maximum profit? We started at $300 profit. Remember, 50 times 6. Let's see how much better this was by just plugging 5 into our function. And we can plug it into any point of our function. We did a lot of simplifying. I'm going to do the polynomial form, because that's probably the easiest. So we have negative 0.1 times 5 squared plus 5 plus 300 on the calculator. And that's going to give us a total profit of $302.50. So we sell 5 additional seats and we make an additional $250. That is our maximum profit. Let's try another example. Number 4. Let's say a fence must enclose an area of 20,000 square feet. The north-south walls cost $2.50 per foot. The east-west walls cost $3.20 per foot. We're going to find the size to minimize the expense. Maybe drawing a picture to help us out here. We don't know the dimensions. We'll say the dimensions are x, y. And so the total area, this is our constraint, total area of 20,000 feet. That means x times y has to equal 20,000 feet. In terms of a cost function, with x and y in it, the north-south walls, those are the x's, and there's two of them, are going to each cost $2.50 per foot. In addition to that, the east-west walls, the two y walls, are going to cost $3.20 per square foot. So for our total cost with xy, we've got 2 times 2.5 is 5x, plus 2 times 3.2, 6.4y. This is what we want to minimize. And our constraint can help us do that. Let's solve our constraint for y. It doesn't really matter which we solve for. And divide both by x, and we find out that y is 20,000 divided by x. And we can stick that in for our y. So now it's just a c of x function. 5x plus 6.4 times 20,000 divided by x. And 6.4 times 20,000, just to make our life easier, is 128,000. So cost is 5x plus 128,000 over x, and I'm going to write that as x to the negative 1. That way our derivative is easy to calculate. So the cost derivative is going to be 5 minus 128,000 x to the negative 2. That's what we want to make equal to 0. I want to notice that x to the negative 2, that's really 5 minus 128,000 over x squared equals 0. And we should be getting pretty good at recognizing that those fractions are going to be really inconvenient. So we're going to clear the fraction by multiplying each term by x squared. That gives us 5x squared minus 128,000 equals 0 times anything is 0. We'll solve by factoring. Factor out of 5 gives us x squared minus 256, or 25,600, equals 0. That's a difference of squares. That's x plus 160, x minus 160. So x either equals negative 160 or 160. However, remember, we're building a fence. We're not going to build a fence that has a side of negative 160. So x is 160. Coming over here to the side, x is 160. That's our first dimension. Y, the east-west wall. Remember, we said that y was equal to, that's a terrible highlight color, y was equal to 20,000 divided by x. So y is equal to 20,000 divided by 160 And when we do that on our calculator real quick, we find out that y is 125. We want a 160 by 125 area enclosed. That's 20,000 square feet. It's going to minimize our expense on the fence. We got everything we want and need. All right, I have one last example to wrap these up. You'll notice every example feels different in the setup because we really have to dig to figure out how to set these up. Once we get them set up, though, they all solve the same. Take the derivative, set the derivative equal to 0, and that's either your minimum or your maximum. That is your absolute extrema. Let's say we have a rectangular garden. Enclosed into 5 sections. And for whatever reason, it has been decided that it's going to be a rectangular garden enclosed like this into 5 sections. The question is, with 1,200 feet of fencing, what is the largest area that can be fenced in? Well, again, we don't know the dimensions of this fence, so let's call it an X by Y fence. What I want to notice is we've got Y on top and bottom, but there's actually several X's all the way through this fence that have to be built. What do we got? 1, 2, 3, 4, 5, 6 X's. 6 X's. In addition, there are 2 Y's, so that total fencing is 6X plus 2Y equals 1,200. That's our constraint. That's what controls us. What we're interested in is the area. We want to maximize the area, which is X times Y. So let's solve the left equation for one of our variables and stick it into the other equation and maximize. We can do this pretty quick. It's probably going to be easiest to solve for y because I like dividing by 2 better than I like dividing by 6. So if we subtract 6x, we get 2y equals 1,200 minus 6x. Divide by 2, and y equals 600 minus 3x. And so the 600 minus 3x is going to go in for the y, and our new area formula is x times 600 minus 3x. Because polynomials are easier to take the derivative of, let's distribute 600x minus 3x squared. And from here it should be pretty routine. Take the derivative and set it equal to 0. The derivative is 600 minus 6x. We make that equal to 0. Add 6x to both sides. Divide by 6, and x is equal to 100. The short side that's repeated over and over again needs to be 100 feet long. We're interested, though, the question's asking what is the area. So we take that 100 and we plug it back into our area function. Area is equal to 600 times 100 minus 3 times 100 squared. When we do that on our calculator, we get an area of 30,000 square feet. That is the maximum area that can be enclosed with the fencing that we've been provided. So a lot of applications today, you're going to see them take a lot of different shapes and forms and sizes. Take a look at the homework. find your equations, take your derivative, set your derivative equal to 0, come to class with questions. We will see you then.